In this video, we're going to talk a little bit about momentum and impulse, and also get into conservation of momentum. To start out, just to define momentum, you probably know just a little bit about it. You could say that momentum is a measure of how hard it is to change the velocity of a moving object. And we need to get straight right up front that momentum is not the same thing as inertia. Inertia is the tendency of an object to resist a change in motion. And many times we think about momentum and we assign its definition to inertia. Momentum specifically has to do with moving objects. You have to be moving to have momentum. You sitting right now where you are, if you are sitting still, you have no momentum if you're not moving. So inertia strictly is mass related. The more mass you have, the more inertia you have, and it has nothing to do with motion. I don't care how fast you're moving, your inertia cannot change, but you can change your momentum by going faster or slower. The formula for momentum, and this goes in the box if you're doing your notes at home, the formula for calculating momentum is this. And you need to be careful how you write it and how you say it, because this letter is not a P, it's the Greek letter rho. Rho is a Greek letter that stands for momentum. That's what we're going to use, and I don't know why whoever it was chose to use rho for momentum, but that's what it is. So it's just something that you're going to have to memorize. The units for momentum we get directly from the equation itself. The equation is mass times velocity. Mass is in kilograms, and velocity is in meters per second. So the units for momentum are kilogram meters per second. So it's not a very hard concept. You can imagine you're driving down the highway in your car. If your car is still, it has no momentum. If it's moving, it does have momentum. And the momentum it has depends on how fast it's moving. And momentum, again, does depend on both mass and speed. The more massive you are, the more momentum you have. And the faster you're going, the more momentum you have. Typically with this part of the course, the only way to really change your momentum is to change your speed. You can speed up, you can slow down. You could change your mass, but that doesn't really happen very often if you're driving down the road in your car, unless you decide to kick your girlfriend to the curb. That's when the mass would change, but it's probably not a very safe thing to do. It won't go very far for you. So the only way to really realistically change your momentum, for the most part, in most realistic situations, is to change your speed. So any object that changes its speed will undergo a change in momentum, and it's really simple to calculate the change in momentum that an object experiences, and that's this formula here. It's really only necessary for us to know the underlying parts of this formula. This is the Greek letter delta. It means change. So delta rho, change in momentum. Remember, rho stands for momentum. Delta rho equals mass times final velocity minus initial velocity. And we simply get that from this term here. The change in momentum is simply the momentum to begin with, subtracted from, or the momentum to begin with subtracted from the momentum that you end up with when you change speed. And because the mass doesn't change, we can actually factor mass out of this equation, and it becomes this equation that we see here. This will be the way that we calculate change in momentum in this class. It's mass times the change in velocity. Alright, so change in momentum, and I want you to imagine, again, you're in your car, you're driving down the road, say you're moving like 70 miles an hour. You're just plugging along. You want to change your momentum, and let's say you're going to come to a stop. Your final velocity will eventually be 0. There's a lot of different ways you can do that, but the two that I want you to think about is this. A, you can either stop almost instantaneously by running into a brick wall, or you can stop safely over a period of 10 seconds by gradually hitting your brakes and letting the car slow down like we normally do. Obviously, most of us would choose the second scenario. And if I ask you the question between those two scenarios, the car hitting the brick wall and slowing down over 10 seconds, which of those two scenarios has the greater change in momentum? I think you might be tempted to say, well, of course the brick wall has a greater change in momentum. But let's remember that we just learned about change in momentum, and to calculate the change in momentum, all that's involved is the mass and the initial and final velocities. So let's remember that, and the truth is that the change in momentum is exactly the same, because the initial velocity in both cases is 70 miles an hour. The final velocity in both cases is 0, and as we said before, the mass doesn't change. It's the same car, the mass is the same. So you undergo exactly the same change in momentum in both cases because the speed change is the same. The speed change is directly related to the momentum itself. In regard to possibly running into that brick wall, which would be a massive collision, we need to talk about the concept of impulse. And impulse is what causes that change in momentum. You've got to have something to cause an object to change momentum. We can talk about that in terms of energy. We can talk about that in terms of Newton's laws, because Newton said that force causes a change in motion. So impulse, it will actually be the product of the force used to change momentum. You got to apply a force. It's that multiplied by the time during which the impulse is applied. And the formula for impulse is this. A lot of times I call this formula JFAT. J equals F delta T, force times time. And J is another new variable that we'll learn. It's impulse. J is for impulse. So we have two new variables for this section. The first one is rho, which represents momentum, and the second one is J, which represents impulse. And the units for impulse most correctly are newtons times seconds, and we get that directly from this equation, force times time, force in newtons, time in seconds. But we'll find out in a little bit that impulse actually, it's not incorrect to report impulse in the same units as momentum, which is kilogram meters per second. So that's impulse. And now let's consider the two situations with the car again, running into a brick wall versus stopping over 10 seconds. I told you that they had the same change in momentum, but suppose I now asked you which one has the greater impulse. You might once again be tempted to say, well, running into a brick wall has a greater impulse, specifically probably because of these words right here, that impulse sometimes can be referred to as the impact of a collision. And of course, the brick wall would have the greater impulse. Well, let's do an experiment about that in a little bit, but before we do, I'd like to work with this equation a little bit and go into the next section of notes. I want to start off with Newton's second law, F equals ma. Okay, we usually write sigma F equals ma, but for now we'll just go with F equals ma. And just stay with me on this for a little bit. I want to do a little bit of algebra. Remember that algebra tells us that we can do anything we want to one side of the equation as long as we do the same thing to the other side, and then the equality remains the same. So let's multiply time by both sides of this equation and see what we get. This gives us ft on one side, and it gives us mat on the other, which may not look like anything to you except when we consider the fact that sometimes we calculate acceleration using this equation, vf minus vi divided by t. So I'm going to take this now and plug it in here for acceleration. And notice what we get after that. Now that looks interesting because this is an understood 1 under this t, which means that these two t's actually will cancel, top and bottom. And that leaves us with something very interesting, especially if I put a delta in front of this t now and make it delta t. This gives us the two things that we just now learned simply by multiplying both sides of this equation by time. We get F delta t, which was the equation for impulse that we just learned. And we get mass times the change in velocity, which was exactly the equation for change in momentum that we just learned. And that brings us to the next set of notes, which is the impulse momentum theorem. And that's in your notes, and that simply puts all of this together. We know that impulse equals F delta t, and we've just proved that that is equal to the change in momentum. So this is a new equation that we're going to learn. This is the most important equation that we'll learn in this entire set of notes, and it's the impulse momentum theorem. And it actually is here. This is where it needs to go on the front side of your notes. So I'm going to write that in here along with you. It's boxed here for you so that that shouldn't be there. So that you'll pay attention to it. It's extremely important, and I know it looks like something that's very long and drawn out and possibly complicated. You'll find that it's really not complicated. It's a very easy tool to use, and I'll explain to you in a little bit just how we use it. Alright, so that's the impulse momentum theorem, but before we get into exactly how to use that, I want to go back a little bit to the example of the car that we're talking about. So here's your car, and it's moving at 70, let's make it meters per second this time, and in this instance it's going to slam into the brick wall. Not fun, right? We said before that whether you hit the brick wall or whether you slow down over 10 seconds, it's the same change in momentum. But what if we ask the question, which one is the greater impulse? You might be tempted to say that this is the higher impulse running into a brick wall because it just seems to make sense. Well, let's actually calculate that. Let's say that the mass of the car is 1,000 kilograms. And I want to calculate the impulse required if slamming into a brick wall, if we come to a stop within 0.4 seconds. All right, so I'll show you how to use this equation by doing this. If I want to know the impulse that's required for this, that's J. Okay, and the thing with this equation that's beautiful is that even though there's 4 parts to it, we'll only ever use 2. So you have to pick 2 parts of the equation. Well, since I want J, that's definitely going to be one part of the equation. So J equals something. And the other part depends on what we're given. Well, I know that the mass of the car is 1,000 kilograms. I know that we're stopping over 0.4 seconds. I know that the final velocity is going to be 0. We're coming to a stop. And I also know that the initial velocity is 70 meters per second. Since I'm giving mass, final velocity, and initial velocity, it only makes sense to then use this part of the equation now. Mass times the change in velocity. And now it gets really easy because all I need to do is plug in my numbers. Final velocity 0, initial velocity 70, and this gives me an impulse of negative 70,000 Newton seconds or kilogram meters per second, whichever you prefer. Both are technically correct in this case. So that's the impulse required when your car runs into a brick wall in order to bring your car to a complete stop. Quite a large impulse, quite obviously. But our question now is which one of these takes a bigger impulse, and many of your hypothesis is that running into a brick wall takes the bigger impulse. Well, let's now consider that we're going to do this the safe way. We're still moving at 70 meters per second, but we're now going to stop over a period of 10 seconds. Okay, we take 10 seconds to come to a stop, and I want to know the impulse that is required. Okay, so the question is, of all of this calculation that I did here, what of this changes? Well, mass remains the same. Time changes. The time now is definitely 10 seconds instead of 0.4 seconds, so that changes. But the final velocity is still 0. The initial velocity is 70, and if I look at all my calculations that I did here, I have the same givens, so I would use the same equation, and I didn't use time in this equation. So actually the impulse for stopping over a period of 10 seconds would still be 70,000 Newton seconds. And that may surprise you that the impulse of both of these quote-unquote collisions, even though this one's not a collision, the impulse is exactly the same. And that brings me back to the impulse momentum theorem. We actually can look at this and see that if the change in momentum in both of these cases is exactly the same, then since change in momentum is mathematically equal to the impulse, then the impulse also has to be the same between these two. So it's the same impulse and it's the same change in momentum. I don't care how long it takes you to stop. I don't care if you stop over 0.4 seconds. I don't care if you stop over 10 seconds. I don't care if it takes you 3 years to come to a stop. It still requires an impulse of 70,000 Newton seconds to come to a stop.